Okay, thanks. Yeah, so this is part 3 of my talk. It's about to thunderstorm outside, so I hope that doesn't cause any difficulties. So I'd like to begin just by, as I did last time, just with a quick recap of things that I said. So we were looking at 3D n equals to 4 gauge theories. They were specified by 2 pieces of data. There was a compact Lie group, which was the gauge group. And then we specified a unitary representation, which is encoding the matter content, the hypermultiplets in the theory. There were some important global symmetries, one of which was the R symmetry, which is always SU2 times SU2. And then there's also a flavor symmetry, which takes again the form of a product, G Higgs and G Coulomb. And there are kind of concrete formula for these things that we described. So the G Higgs depends very much on what the matter representation is. It's essentially the kind of symmetries that are left over once you've gauged G. And then the topological, the Coulomb branch symmetry is a bit harder to describe, but there is at least an abelian subgroup called the topological symmetry, which is basically the center of the Langlands dual of the group G. Okay, so that was the first lecture. The second lecture, we introduced some important deformations of this theory. So these, the way I phrased them were as scalar central charges, central extensions of the supersymmetry algebra. But physically, they're mass parameters and Fi parameters. And the mass parameters are valued in the Lie algebra of the Higgs flavor symmetry, and the Fi parameters are valued in the Lie algebra of the Coulomb flavor symmetry. So the numbers of these parameters depend pretty much on the data, what the gauge group and the representation is. And a general theme that I'd like to emphasize is that many interesting constructions in these theories fiber in an interesting way over the parameter space of mass and Fi parameters. And it's an interesting thing to do, to ask how observables, they might, they might be vacua, they might be other complicated things like line operators or boundary conditions. How the sets or categories or whatever of those things, how they depend on the masses and the Phi parameters is an interesting question. So what I talked about was mainly the vacua. And so we made a kind of crucial assumption, which was that if you look at very generic values of these parameters, then there are only discrete isolated vacua. So, the system sits in a massive vacuum, basically. But on the other hand, if I go to some special loci, codimension 1 loci, then, and these are basically the loci where kind of domain walls between these vacua become tensionless. If I go to those loci, then I can get a moduli space opening up, an extended moduli space of vacua. And that's what I'd like to talk about in today's lecture, is to speak a bit more about these moduli spaces that open up and what mathematical structures they have. Okay, so indeed, what's the general structure of supersymmetric vacua? And in general, it's a very complicated. There are kind of 2 extreme cases. The first case is the one that I discussed last time, which is where you make everything generic and you just have some discrete set of vacua. In the opposite limit is where you set the masses and Fi's to 0. And this is sometimes called the superconformal point. And then you have a very interesting, kind of more intricate moduli space of vacua with various branches that intersect in various ways. And that's also an extremely interesting thing to study. But it's in some sense the hardest part, is to go all the way down to the origin of the space of masses and Fi's. What I'd like to focus on today is kind of 2 intermediate cases. So the first is where you set the masses to be 0, but on the other hand, you let the Fi parameters be generic. And then a moduli space opens up, which is what we call the Higgs branch. And then on the other hand, we can do the opposite thing. We can set the mass oops. You can see that there's a typo there. Part 2 should be, if I set the Fi parameters to be 0 and the masses to be generic, then a moduli space opens up, which is what we call the Coulomb branch. And this is the origin of these subscripts that I've been putting everywhere on the R symmetry and the flavor symmetry. And we do that basically because these symmetries will act on these moduli spaces. Okay. Good. So that's what I'd like to talk about today. So let me just give a bit of a broad picture, a summary, if you like, of how this fits in with everything that I said before. So so here, of course, if I set the mass to 0 and I keep the Fi generic, I could then imagine turning the mass back on. I should recover what I did in the last lecture. And so, if I start out with my Higgs branch X, say, and then I turn back on the mass, I should arrive back at a situation where I have a discrete number of vacua. And similarly, if I start with this Coulomb branch and then I turn back on the Fi parameter zeta, then again, I should recover this discrete set of vacua. And we should understand how that happens. In the opposite limit, if I start with the Higgs branch and I take zeta to 0, what happens is that the moduli space develops a kind of conical singularity. And these conical spaces, they form part of this this bigger intricate structure that you get at the origin of the space. Okay, so I'd like to describe some of those things today. Let me just, before I do that, I figured it would be good just for those people who perhaps are wondering about the labels, Higgs and Coulomb. So let me just tell you what that indicates. So these labels, Higgs and Coulomb, are to do with the kind of infrared behavior of the gauge theory. If you're at a point on this moduli space and you look at the low energy behavior of the gauge theory, then Higgs and Coulomb are referring to the type of behavior. So Higgs branch generically means something where the gauge symmetry is broken and the matter fields X and Y have non-vanishing expectation values. On the other hand, a Coulomb branch is somewhere where the gauge symmetry is typically broken to a maximal torus. So it's an abelian gauge theory. That's why we call it a Coulomb branch. And the hypermultiplets vanish. So this is typically what the behavior will be like in each of these branches. And that's why we call them that way. Okay, so I'd like to discuss well, maybe I can stop for some questions there. Otherwise, I'm going to move on to talk about the Higgs branch. So are there any questions at this point?
There's a question in chat. Only real Fi parameters and masses?
Yeah, indeed. So indeed. So just like yesterday, in principle, I can turn on both real and complex masses and ask exactly the same questions. But just for the purpose of my talk, I'm going to focus on a slice of that picture where I just turn on real and masses and Fis. But one can do the others if you like as well. Good. Okay. Okay, so I'm going to discuss the moduli spaces in turn. So I'm going to begin with the easy one, which is the Higgs branch. Okay, so when do we have a Higgs branch? Well, to get that, we need to set the mass parameters to 0, and we take the Fi parameter zeta to be generic. And so just a reminder of last time, what generic means is, well, we have these hyperplanes in the parameter space of Fi parameters, and we just want to make sure that we stay away from any of those. So we sit inside a chamber in the complement of these hyperplanes. So that's where we want to sit in the parameter space. So to see the Higgs branch, we can just, as we did last time, we can look at the equations, the classical equations for vacua that you get just by minimizing the classical action of the theory. And we can just set the mass to 0 in those. So again, they look something like this. The top line involves the moment maps, the real and complex moment maps for the action of the gauge group on the hypermultiplet representation. And then you've got the remaining equations involve the vector multiplet scalars. Sigma is a real scalar and phi is a complex scalar. So again, here, everything on the left is a real equation and everything on the right is a complex equation. And so this simplifies dramatically for the following reason, which is under the assumptions that I made last time, which is exactly the condition that for generic values of these parameters, I have only isolated vacua. Under that assumption, then the solutions of these equations all have to have sigma and phi vanish. And moreover, the gauge group is completely broken. And again, the intuition, I don't want to give a detailed argument, but the intuition here is that the matter representation should be big enough so that there are enough hypermultiplet fields x and y such that these middle equations here, together with the sometimes the real moment map equation, kind of force sigma and phi to vanish. You know, if x and y are generic enough, there are enough non-zero x's and y's, then that will force sigma and phi to vanish. So in other words, we can scrap the bottom 3 lines and focus on the top 2. And the top 2 lines describe exactly what's called a hyperkähler quotient. So in other words, the Higgs branch, it's parameterizing solutions to these 2 equations. You set the real moment map equal to the Fi parameter and the complex moment map to 0, and then you divide by gauge transformations. And this is what's sometimes called a hyperkähler or a holomorphic symplectic quotient. Okay, so I'll describe a bit more what that means in a second, but let me just make an important point, which is that in a supersymmetric gauge theory, which has a Lagrangian, there are non-renormalization theorems, and which ensure that this picture is exact, that there are no quantum mechanical corrections to this picture. After all, we derived it by essentially trying to minimize the classical action, but in this case, one can show that it's really exact. Okay, another way to say that is that the Higgs branches of gauge theories are quotients, finite dimensional quotients. Okay, that statement will not be true for other branches. Okay, so let me give a bit of geometry, a bit of background. So this type of hyperkähler quotient, although I assumed from the outset that this representation was of cotangent type, I didn't have to do that. It can be defined for any quaternionic representation, and it outputs a hyperkähler manifold for you. I'm not going to explain what that is too much because I want to restrict to representations of cotangent type, and turning on parameters, it's more natural here to view things rather as what's called a holomorphic symplectic manifold. So indeed, if the representation is of cotangent type, and so I imagine that I have kind of complex coordinates, x and y, it's more natural to regard X as a complex manifold together with 2 additional structures. So the first is a Kähler form, and this is a closed 1-1 form, And it's the thing that you get, it's kind of inherited, or it's the image under the quotient of the natural Kähler form that I had on T star of on the cotangent bundle of the representation. So it's the thing that looks like this. And likewise, this space also has a holomorphic symplectic form, which is a closed 2-0 form, which is inherited from the one you get by taking dx wedge dy. Okay, so we can think about it in this way, as a complex manifold together with these two additional pieces of structure. And I should say these pieces of structure are important for the physics. I mean, they go into, for example, if you were to flow to a sigma model onto the target space of this thing, both of these structures would enter there and specifying that theory. Okay, you can see that there's a comment. Yes, indeed, Jacques is reminding me that for this to be a Kähler form, I should really put an I in front of the expression. Yeah, I'm being a little lazy here. Thank you. Okay. So before I give an example, let me just give a kind of cartoon picture as to how to think about these spaces. So again, under our assumptions, if the Fi parameter is generic, then the space that I get is a nice, smooth, holomorphic symplectic space with these structures. And then what happens is, as the Fi parameter tends to 0, is that the space becomes kind of conical. It develops a singularity, and if I sit at that singularity, then the gauge symmetry is unbroken there. And then at that point, I might have other moduli space, other components of the moduli space coming off. And this thing forms, some piece of a much larger moduli space at that point. Okay, so this is just a cartoon. Let me give an example. So let's look at supersymmetric QED. This was the case where the gauge group is U1, and I had just W hypermultiplets. So the two equations looked like this. There's a real moment map equation, a complex moment map equation. In this case, there were just W fields X of charge 1, W fields Y of charge -1. And the equations look like this. So let me try to describe what this space looks like. So let's first imagine that I set the Fi parameter to be positive. Then a first thing I can do to get some understanding of this space is that I can just look for solutions where Y is 0. If you try to look for a solution where X is 0, then obviously the first equation can't be solved. So let's just look for solutions where Y is 0. In that case, the real equation just looks like this, and that describes a sphere of dimension 2W - 1. Okay, because I have W complex coordinates, that's 2W real coordinates, and I'm setting the sum of their squares equal to a constant. And then if I divide by gauge transformations, well, that's like taking the quotient along the fibers of the Hopf vibration. And the space that I end up with is a complex projective space of 1 dimension less, so CPW -1. If you think about this algebraically, you can roughly think about the x's as kind of homogeneous coordinates on the complex projective space. If I then try to put back in the y coordinates, well, I've got the complex equation here, and that, just like that kind of tells you that the y's want to be in the cotangent bundle to whatever the x's are. And indeed, the whole space is given by the cotangent bundle of the complex projective space. So that's an example. And that was the case when zeta is positive. If it's negative, the result looks pretty much the same, except you exchange x and y. The interesting thing is what happens when zeta is 0. This is kind of the hyperplane. So in this parameter space of fi parameters, in this case, it's just a real line. There's a single fi parameter. And the only hyperplane I have to worry about is the origin. And what happens at the origin is that the space that I get is well, it's what's called a closure of a minimal nilpotent orbit. And well, let me just say the following. You can build a natural set of gauge invariant operators, which are these mesons. You know, x has charge 1, y has charge -1. So if I take their product, in this case, I'm going to get a W times W matrix of gauge invariant operators. And the constraints imposed by the equations you can check tell you that this matrix has to give you an element in the minimal nilpotent orbit inside SLW. So this is a conical space, and when you turn on the fi parameter, you're resolving it. So the picture, you know, a slice of this thing looks like this here. So we've got a real line. If the fi parameter is positive or negative, I get a copy of the cotangent bundle of projective space. And then at the origin, I have a closure of a nilpotent orbit. Okay. Good. So this is an example. Are there any questions about this example? Or anything else? Okay.
So far.
Okay. All right. So what I'd like to do now is to explain a bit how we can view symmetries from the point of view of the Higgs branch. So physically, if I turn on, if I set the masses to 0 and I turn on a generic fi parameter, what's going to happen is that the theory will flow to a sigma model whose target space is the Higgs branch, this space X. So it's a theory of maps from space-time into X. And I'd like to try to understand how the global symmetries are realized in this sigma model. So in particular, there's the R symmetries, and there's also the flavor symmetries. And another thing we'd like to do is to kind of reintroduce the mass parameters. And when I do that, I should recover the isolated vacua I had before, and these nice hyperplane arrangements in the space of mass parameters. I'd like to see how I can recover those and think about them in the sigma model point of view. Okay. So let me first discuss the R symmetry. And so, well, one general lesson is going to be that many flavor symmetries are going to be, well, global symmetries are going to be reflected in the geometry and topology of the moduli space. And so we want to see how that happens in this case. So let me first discuss the R symmetry. And so the top line is for those of you that know about hyperkähler geometry. So if we think about X as a hyperkähler manifold, then this SU2 Higgs R symmetry, it acts by isometries of the hyperkähler metric that rotate the CP1 family of complex structures. Let me try to say that in a more pedestrian way in terms of this holomorphic symplectic picture. So in this case, let me just focus on the Cartan U1 Higgs. Actually, that's the only thing that well, okay. And this acts by isometries of X. If you like, we saw in the last lecture that the U1 Higgs R symmetry, it acts on the fields, the coordinates X and Y, in the following way. And I can see that I've made a really bad typo here. It should rotate X and Y in the same way. So this minus sign here should be a plus. Sorry about that. And so basically you're kind of, you're factoring through how this acts through the quotient. And so, and the U1 Higgs symmetry acts in this way. And the first thing to say is that this symmetry leaves the Kähler form invariant. In fact, it's a Hamiltonian isometry. On the other hand, it transforms the holomorphic symplectic form non-trivially with weight 1. So the holomorphic symplectic form transforms like this. One way to see that is that the holomorphic symplectic form was just dx wedge dy under the quotient. And indeed, if I hadn't made the typo, then it would transform in this way. Okay, so that's how I can see the R symmetry. It's a Hamiltonian isometry that, that transforms the holomorphic symplectic form with weight 1. Okay, question. Yeah, exactly. It's Hamiltonian with a real moment map. So yes. So what I mean by that is that you know, omega is invariant. If I contract with the vector field, that will be d of a real moment map. Okay, so let me then also describe the Flavor symmetries, T Higgs and T Coulomb. And again, they're going to be reflected in the kind of geometry and the topology of the moduli space. So let me first describe the topological one, which is interesting. So the topological symmetry, perhaps not surprisingly, is recovered from the topology of X. And in particular, you recover the Cartan subalgebra as a vector space is just given by the second homology of X. So this is something that's really special to 3 dimensions. If I were to do this in 4 dimensions, I would get a 1-form symmetry. In 5 dimensions, I would get a 2-form symmetry. The reason here is that if you take a 2-form on the target and pull it back, you get a codimension 2 operator, which generates a symmetry, a 0-form symmetry. But okay, so we can recover the topological symmetry here from the topology of the space. On the other hand, the Higgs branch flavor symmetry is again given by Hamiltonian isometries of the target space. But this time, the Hamiltonian isometries that leave the holomorphic symplectic form invariant. Okay. If you want to say that in a hyperkähler way, these are kind of tri-Hamiltonian isometries. So this kind of explains the subscript H on the R symmetry and on the flavor symmetry. It's H because these are symmetries which act by isometries on the Higgs branch. And the same will be true in the other way around when we look at the Coulomb branch. Okay. So we can get the flavor symmetries here from a sigma model perspective. Let me just give an example for a sanity check. So we just saw in supersymmetric QED that the target space was the cotangent bundle of complex projective space. So in this case, to recover the topological symmetry, in this case, the second homology is just generated by the class of the base. And so it's just R. And this disagrees with the fact that the topological symmetry is just U1 in this case. There's a single generator. On the other hand, if I look at the Hamiltonian isometries that preserve the holomorphic symplectic form, they're exactly given by PSU. And again, this is a typo, it should be PSUW. Sorry about that. these are the isometries of complex projective space, basically. Okay, I think there's a question in the chat. Yeah, thanks, Aswin. Yeah, that's absolutely right. In the previous slide, yeah, I mean, TH is was the Cartan. Sorry, was the maximal torus of the flavor symmetry, and that's a maximally commuting set. But I could have, as you say, I could have just written GH, and that would have been the group of Hamiltonian isometries of X. Yeah, thank you. So yes, you can see the full flavor symmetry. Good. Okay, so that was an example. That was a sanity check that things are working out. Okay, good. So let me now try to explain how to reintroduce mass parameters. So up to now, in this point of view, I've set the mass parameters to 0. I've turned on the Fi parameters in order to flow to a sigma model onto the Higgs branch. And what I'd like to do now is to reintroduce the mass parameters from a sigma model point of view. And so from that perspective, you're turning on a massive deformation of the sigma model. And it's a deformation that depends on a real superpotential that I call H sub m. And that's very much analogous to the real superpotential H that we talked about in the gauge theory. It's really the sigma model version of that. And what is it? Well, it's m, the mass dotted that I'm introducing, dotted with the moment map for the Hamiltonian isometry, the T Higgs Hamiltonian isometries. Another way to say that is that H itself is just the real moment map for the Hamiltonian isometry that's generated by the mass parameter. So I think of the mass as it's an element of the Cartan, it's generating an infinitesimal isometry, and this is the moment map for that. Okay, so this is actually this is actually a perfect Morse-Bott function. Doesn't matter too much, but the point here is that it introduces a from a sigma model point of view, it kind of introduces a potential into the theory. It introduces a potential term that's like mod squared of d of the derivatives of this function h. And so it's trying to localize things in the sigma model onto critical points of the function h. So the effect of that is that it's if I introduce masses into the theory, in the sigma model point of view, it's going to the remaining kind of supersymmetric vacua will just be the critical points of this function h sub m. Now, precisely because h is the moment map for an action on a Kähler manifold, then this is equivalently another way to say exactly the same thing, is that these are also the fixed points of the isometry that's generated by the mass parameter. So you can say it in either of those two ways. And we can recover exactly the same structures we saw in the gauge theory from a sigma model point of view. In some sense, it's kind of a special case. So just like before, if the masses are very generic as possible, then the critical locus of this function will just be a bunch of isolated points, which you can identify with the supersymmetric vacua. And again, I call them VA, V alpha labeled by some discrete index alpha. And now I think about them as really points on the Higgs branch. But just like before in the last lecture, if I want to study kind of what it means for the masses to be non-generic, where moduli space opens up, then one way to do that is to think about domain walls that interpolate between the two vacua. So for example, we can imagine a domain wall in the filling the x12 plane that interpolates between, a vacuum VA and a vacuum VB. And if I want a domain wall that preserves 2,2 supersymmetry, then these are given by gradient flows for this function h. So here I would look at a gradient flow that starts at the critical point alpha and ends at the critical point beta. And again, like before, the tension of such a domain wall is given by basically the difference of this function h at the two vacua. And when this vanishes, that indicates that a moduli space is opening up that connects those two vacua. And we get a nice picture in this case of what that moduli space is. It's just the critical locus of the function h, m, when I specialize m to sit on that locus. It's just that, as m becomes more and more specialized, the critical locus gets bigger. And we're asking when that happens. And it happens at exactly the same places as it does in the gauge theory construction. In particular, there are these hyperplanes labeled by pairs of vacua, where the critical locus jumps, it suddenly gets bigger. And it's a non-trivial fact, but that this reproduces the same hyperplane, the same results as you get in the gauge theory answer. Particularly if you evaluate this real superpotential H in the gauge theory at a vacuum, you'll reproduce the same result by evaluating the moment map in the vacuum here. Okay, so we can reproduce the whole this nice hyperplane arrangement from this point of view. Okay, I think that's all I want to say about the Higgs branch. So maybe again, I'll just pause and see if there are any questions.
So far, it looks. Well, we've got several questions already, to be fair. So just not that great.
Okay, so then let me talk about the Coulomb branch. And in many ways, on general grounds, if I just think in terms of geometry, everything about the Coulomb branch is going to be identical, except that everywhere I exchange Higgs with Coulomb, I exchange the subscripts H and C, and I exchange the role of the masses and the Fi parameters. Because there's, throughout these lectures, there's been a whole symmetry of the problem. But how that actually arises, or how to check that in detail in a supersymmetric gauge theory is remarkably tricky. And the reason is because in contrast to the Higgs branch, for the Coulomb branch, there can be very non-trivial quantum mechanical corrections to the classical picture.
Mathew, before you go on, it looks like there's a quick question on the slide. Does the potential H get quantum corrections?
Yeah, thank you. Good question. Not with this amount of supersymmetry, no. So if you remember last time in the gauge theory, so let me just say, if I were to look at theories with half the amount of supersymmetry that I have here, so like 3D n equals to 2 and say 0, 2 domain walls, then there would indeed be one loop corrections to the tension of a domain wall. But with the amount of supersymmetry I have here, they don't arise. Another way to say that is the following. If you look back in the gauge theory perspective, this function h was basically a mixed Chern-Simons term between T Higgs and T Coulomb. Now, the mixed Chern-Simons terms involving T Coulomb are essentially classical from a sigma model point of view. Now, if I go to a theory with less supersymmetry, this function h will receive contributions from all possible mixed Chern-Simons terms in a vacuum. And as you know, as we know, like when you integrate out matter, you can the mixed Chern-Simons terms you get from a one-loop quantum correction. And indeed, so when you flow to a sigma model and view it from this point of view, in the sigma model, there'll be one-loop corrections to the tension of domain walls. But with double the supersymmetry that I have here, then there are none. They cancel out. It's essentially the statement that there are no. I should have said it. Another way to say it is that there are no Chern-Simons terms that preserve n equals to 4 supersymmetry, except between vector multiplets and twisted vector multiplets. Okay. Thanks for the question. All right. Good. So for the Coulomb branch, I'd like to now talk about the Coulomb branch, and life is opposite. This is a direct copy of the slide for the Higgs branch. I now want to set the Fi parameters to 0 and take the masses to be generic. And again, like before, generic means that I lie away from any of these bad hyperplanes in the space of masses. And I can play exactly the same game as I did before. So I can try to study the equations for classical vacua, except this time I set the Fi parameters to 0 rather than the masses. So now in the top line here, the Fi parameters have gone, but I've got the masses appearing in the second and the third line. And this time, under our assumptions, if M is generic, then the kind of the opposite happens. This time, the only solutions have X and Y 0. And moreover, I can solve the final line. So that basically, that basically solves the top 3 lines, if X and Y are 0. The bottom line is solved by asking sigma and phi to lie in a common Cartan subalgebra. And moreover, for generic values of the vector multiplet scalars sigma and phi, the gauge symmetry will be broken to a maximal torus T. So again, this is why we call it a Coulomb branch, because it looks like an abelian theory in the infrared. Okay, so you might think from this point of view that that sigma and that the moduli space is just parameterized by sigma and phi. That can't be true, because that would only give us 3 real coordinates: sigma, one real coordinate sigma, and one complex coordinate phi. But we know that the whole situation was very symmetric, and so we know that the space that we get should it should be hyperkähler, so it should have real dimension that's a multiple of 4. So where does that extra coordinate come from? Well, there's one thing we forgot about, which is the gauge connection, A. And so let me assume for a moment that that I sit at kind of a generic point for sigma and phi, and so the gauge symmetry is indeed broken to a maximal torus, an abelian symmetry. Then each of the abelian gauge fields can be dualized. You can take to a periodic scalar called gamma, and we often call that the dual photon. So it's related to the gauge field by this kind of relation here. Okay, that makes sense, because A is a connection, which is a 1 form. Its curvature dA is a 2 form. If I take the Hodge star of that, that's a 1 form again. And if I write that as d of something, then that something should be a scalar. And if you do things carefully, this scalar should be periodic. So what that suggests is that kind of near generic values of sigma and phi, where this is true, the Coulomb branch is going to look roughly like R3 times S1 for every generator of the Cartan subalgebra. So R3 times S1 to the rank of the gauge group, which is just parameterized by all of these scalar fields. So this is the kind of classical picture, but it receives, very dramatic quantum mechanical corrections. In particular, it can receive both one loop and non-perturbative quantum corrections. So let me give a very brief kind of history of these things. So indeed, the Coulomb branch receives very strong, interesting quantum mechanical corrections. So when G is abelian, if I look at an abelian gauge theory, there are only one loop corrections, perturbative corrections. One way to understand this is that there are no, the quantum correction, non-perturbative quantum corrections would come from kind of dynamical monopoles, and there are no dynamical monopoles in abelian theories. And so the corrections are only perturbative and one loop. And they were completely understood, basically, in the 90s by Seiberg-Witten, Seiberg and Trillagator and others. And so you can really, in an abelian gauge theory, you can really write down the hypercalometric and understand fully the Coulomb branch. When the group is non-abelian, you can also get non-perturbative corrections, which, as I said, come basically from like dynamical monopoles. And they're much more tricky to compute. And so, for a long time, a lot of progress, I think, was made by making predictions using string theory, brane constructions, mirror symmetry, things like that. And it's only relatively recently that kind of more rigorous field theory progress has been made on understanding at least some aspects of the Coulomb branch. And that uses techniques more from algebraic geometry. So it's something that tells you about the Coulomb branch as an algebraic variety, or perhaps a symplectic algebraic variety. And I'm not sure, but I suspect certain aspects of that will be discussed in some of the other lectures in this summer school. Okay, so I'm not going to discuss that in detail in my lectures. That would be another course, I think. So let me instead just give you an example to see what things look like. So let me continue with my example that I followed throughout the lectures, which is supersymmetric QED. So in this case, the gauge group has rank 1. It's U1. And so the classical result would just be R3 times a circle. So R3 being parameterized by the three scalars and the vector multiplier, and S1 by this dual photon. That's the classical result. But if you take into account the quantum mechanical corrections, which are just one loop in this case, then the correct result is that the Higgs branch is actually a resolution of an A-type singularity, a Kleinian singularity. So you take C2, you take the orbifold C2 mod ZW, and then you resolve it. Let's see, maybe there's a question. Are there upper bounds on the gauge group rank? No, I don't think so. Okay. So good. So just to illustrate the kind of what these quantum corrections are doing, let me try to draw a picture of the classical and the quantum corrected Coulomb branch in this example. And let me, so that I can draw it in a simple way, let me do two things. First, focus on the case when W is 2. So this is super QED with 2 flavors. And let me just focus on a kind of section, a real two-dimensional section where I set phi to 0. So in this case, what I'm plotting here is the real scalar sigma running from left to right. And then this circle is the thing that would be parameterized classically by the dual photon. So on the left, I've got the classical picture. This section is just the real line times a circle or a cylinder. What the quantum corrections are doing is at the values of the masses of the hypermultiplets, it's causing the fibers, the circle fibers, to shrink to 0 size. And so what you get in this case is actually, I mean, this is a picture of the cotangent bundle of CP1, which is a resolution of this A-type singularity, C2 mod Z2. And indeed, you can see here that if I take the masses to 0, this P1 is shrinking, and I get the singular space in that limit. Okay. So again, let me just emphasize that the general structure of X is the same essentially as the Higgs branch, with all of the labels exchanged. So in particular, for generic values of the masses, it's going to be a nice, under my assumptions at least, it's going to be a nice, smooth, holomorphic symplectic manifold, whose complex dimension is given just by the rank of the gauge group. The dimension, at least, doesn't depend on the matter representation. And again, just like before, it becomes conical as I send the mass to 0. And part of this larger moduli space that you have. And again, the flavor symmetries can be recovered in a similar way. So this time, it's the Higgs branch flavor symmetry that is recovered from the topology of the space, from H2. On the other hand, the Coulomb branch symmetry, flavor symmetry, acts by isometries of the Coulomb branch. That preserve the holomorphic symplectic form. So again, this is why these things have the label C, because they're symmetries that act on the Coulomb branch. Okay, so in the last 5 or 10 minutes, I want to talk about a couple of things, and this is really just to give you a hint of where things can go, and kind of active research directions, and what people might be working on in this field. So the first thing I'd like to talk about is symplectic duality. And so, well, first there's an observation, which is that what we've done is to any supersymmetric gauge theory, 3D n = 4, we've assigned 2 spaces, the Higgs and the Coulomb branch, X and it's, yes, the Higgs and the Coulomb branch. And we've seen that many features of the theory, many properties, can be understood equally from the perspective of both of them. For example, the flavor symmetries we've just discussed. The Higgs branch flavor symmetry is, well, it's isometries of the Higgs branch or topology H2 of the Coulomb branch. The Coulomb branch symmetries, there's a typo here, it should be TC, are given by Hamiltonian isometries of the Coulomb branch, or equivalently, topology H2 of the Higgs branch. We can also look at the supersymmetric vacua. We computed them in the gauge theory when they're isolated, and we could view them in 2 ways. We can think of them as fixed points on the Higgs branch, or we can think about them as fixed points on the Coulomb branch. And those 2 things have to give the same answer. And that goes even further. There's this very nice central charge function, or effective in the gauge theory point of view, this is the effective Chern-Simons coupling between T Higgs and T Coulomb. And we computed that in the gauge theory. And you can also get it from the sigma model to the Higgs branch by studying the value of the moment map for isometries. Or you can do it, you can get the same thing from the Coulomb branch, again, by studying the value of the moment map at fixed points for isometries of the Coulomb branch. And these are very different computations, and yet they have to agree. And so a pair of spaces that have these properties and more are sometimes called symplectic dual. And this is an idea that was introduced by, I can see that I've made a typo in the authors here. I apologize for that. So this was a concept that was introduced in representation theory. Sorry, this should be Braden, Licata, Proudfoot, and Webster. And the basic idea is that if you can find observables that you can describe equally well from the perspective of a sigma model to the Higgs branch and a sigma model for the Coulomb branch, that's going to give you a non-trivial equivalence of some interesting mathematical structure associated to those two spaces. And so this idea is called symplectic duality, and it has kind of important applications in representation theory. And it's an active area of research, trying to understand various mathematical constructions that you can attach to these two spaces that are equivalent in a non-trivial way. I think I saw there was a question. Okay, let me leave that to the end. Okay, and then a related, but I think distinct phenomenon is that of 3D mirror symmetry. And this is an infrared duality. So it's a situation where you have two theories, which could be two supersymmetric gauge theories, which flow to the same superconformal fixed point, kind of in the absence of mass and Fi parameters, but with the flavor and the R symmetries exchanged. So it's an example of an infrared duality where you have two, say, UV gauge theories that flow to the same fixed point. And this has the property that it exchanges the Higgs and the Coulomb branch of the two theories in this way. And this can be a really powerful idea because if you know the pair of mirror theories, for example, you can build them using string theory or brane constructions, and one of the branches is much harder to describe than the other, then you can compute, say, the Coulomb branch in one theory by computing the Higgs branch in the mirror. And if you have some handle on what the mirror is from brane constructions or something else, then that can be a very useful and powerful thing to do. Okay. So I think that's all I have to say. My time's up. So thank you very much for listening, and I'm happy to answer more questions.
First, let's take a minute to thank him with our reaction points. And then questions. I think Aswin had a question in chat. Aswin, let me see if I can make it possible for you to say it loud. I can find you in the list. Well, I can do this.
I can ask the question. I think I was already able to unmute.
Yeah, I think I agree with Aswin's comment. Yeah. Okay, so there's a question which is, could you give an idea of what extending it to QCD looks like? And the answer is yes. So I'm not sure exactly what aspects, but I mean, So QCD might be where you have the gauge group being UK, a higher rank unitary group. And again, you take the representation to be some number of copies W of the fundamental representation. So let me just describe the Higgs branch in that case. The topological symmetry would again be U1, so there's a single Fi parameter. And if the Fi parameter is non-zero, instead of the cotangent bundle of projective space, you would get the cotangent bundle of a Grassmannian in the case of super QED, super QCD. And whereas if you take the Fi parameter to be zero, that would be a you would get a closure of a non-minimal nilpotent orbit in SLW. So that's what the Higgs branch would look like. If you want to know what the Coulomb branch looks like, I can't quite remember a neat way to phrase it off the top of my head. One thing which I know that it is that it will be a moduli space of singular monopoles, singular SU2 monopoles. That's one way to say what it is, but it's something that one can find explicitly. Okay, thanks.
This one has his hand up, and then there's also some more questions in chat.
Yeah, so there's some more questions about the rank of the gauge group and swampland conditions, and yeah, I think I'm going to appeal to Jacques' answer there. Yeah, I'm just doing field theory. I'm not asking about consistency with coupling to gravity at the moment.
So Matt, I had a quick question about some of the more recent algebraically minded works. I say you take something like the coordinate ring of any of these varieties. How does that change, say, when you have generic FIs, zero masses, or say the other way around for the Higgs or Coulomb branches?
Yeah, well, the coordinate ring doesn't really detect the real parameters, right? It's just yeah, it doesn't really see the real parameters. So another way to say it is that like the Fi parameter, for example, is a Kähler parameter. So if you're just looking at complex functions on the space, you won't, or algebraic functions, you won't see it. As an algebraic variety, it doesn't care about the real Fi parameter.
So, but if you had complex masses or complex FIs, that would change.
Yeah. So indeed. So if you put on that would indeed change if you were to turn on a complex Fi parameter. Indeed, that you would see it. Yeah. Absolutely. Yeah.
And I mean, you mentioned the sort of intricate structure that these moduli spaces have when both the parameters are set to zero, right? There are many strata, there's closure relations, and so on.
Yeah.
So is any of that remembered when you have generic values? Like, do the points mean something? Do they know something from the? Do they remember anything from the stratification data or something?
I mean, I think. Yeah, I mean, I think that in some sense, when you go to non-generic values, that's maybe intermediate between generic and, say that I land on, one wall or, intersection of two walls or something, then I'm kind of seeing pieces of that structure. It's kind of isolating pieces of that space. But I don't know a more systematic way to say that.
Hi. So I was just wondering what's known about BPS states and their wall crossing in these 3D n equals 4 theories, if it happens at all.
Good question. Yeah, so first we should say what we mean by BPS states. We could mean a bunch of things.
Yeah.
But yeah, so for example, one thing that you can do is you could put this theory on, you know, let me say one thing where that I know what to do. So you could try to put this theory on a curve, say a Riemann surface, or an elliptic curve, and think of it as a quantum mechanics.
Right.
And then think of BPS states as ground states of that quantum mechanics. And those spaces can indeed undergo wall crossing, as you kind of as you cross over the walls in what I've been describing. And I think Hyun Kim will talk a bit about that in her research talk later in the school. So we had a recent paper about that in the case of when you put it on a curve and you do a kind of topological twist. You can also do it on an elliptic curve with like Ramon boundary conditions, and then you get a very nice story there as well.
I see. Is there any reason to go to a compact curve and not just work on R2 with some vacuum?
Yeah, you can also, yeah, indeed. So you can also work on R2 with a vacuum at infinity. That's something you can do. You can study the Hilbert space of that problem, which is, well, you know, the half BPS states in that problem. And you can even understand how operators in the theory act on that Hilbert space. And we studied that in a paper with Tudor de Mofte, Davide Gatto, Justin Hilburn, and Hee-Chol Kim, called Vortices and Vermas.
Okay, thank you very much.
There's a nice connection. There's lots of nice connections to representation theory there as well.
Okay, thanks.
Are there any other questions? I don't see any other hands raised, and I don't see anything else in chat. So I think that's it. So let's all thank Mathew for giving extremely nice set of lectures.